Alright, so here we have another attempt. We're trying to adjust the lengths. So in this case we've subtracted some number a and added it to two of the sides. And we're looking if there's any number of a that exists so that this cuboid has the exact same volume as the cube. Right, remember the volume of the cube is p cubed. Alright, so to test this, we could equate the volume of the cube to the volume of this cuboid. So the volume of the cuboid is p minus a times p plus a times p. Which we can expand and simplify. P times p, p squared, p times a, plus ap, minus a times p, minus ap, minus a times positive a, minus a squared. All of that's still times p. These middle two terms cancel out. And then we're left with p squared times p cubed, minus a squared times p. So that's the expression for the volume of the cuboid. And we want to see if there are any values of a that make this equal to the volume of the cube. Volume of the cube. Does it ever equal the volume of this cuboid? Right, now remember this cuboid is just defined as having some number added to one length and that same number subtracted from the width. Right, and the height remained the same. So let's now solve this equation. So we could subtract p cubed from both sides, and we're left with 0 equals minus a squared p. Okay, interesting. So can p equal 0? If p equals 0, this height here would be 0, so it wouldn't be a cube, right? So p cannot be equal to 0. But for this to be equal to 0, so minus a squared times p equaling 0, a must be 0, right? Because if a is 0, 0 squared is 0, 0 times p is still 0. So a equals 0 is the only solution since p cannot be equal to 0. Again, if p was equal to 0, we wouldn't have a cube, so it's pointless. So if a is 0, that just says that the volume of the cuboid is the same as the volume of the cube when the cuboid is the cube. Alright, it's kind of pointless. We already knew that. So adding and subtracting a number from two sides doesn't work.